Pretend I have d vectors, all of which are n-dimensional. Okay, so to clarify the difference between d and n, I have d vectors, each has n components. A linear combination of these vectors is just any vector that I can express as number times the first vector plus number times the second vector plus number times the third vector, and so on. And now here, I've expressed my set of vectors that I'm dealing with as v1, v2, and so on and so forth, which at first glance might be a little confusing, because on the last slide and a few slides ago, v1 and v2 and v3 represented the components of one vector, and those are scalars. Now v1 is a vector on its own, and v2 is another vector. Okay, and I'm intentionally using notation that forces you to think about what exactly it is you're dealing with, because I don't want you to memorize like v1 is the first component of a vector. Well, v1 could be a vector, it could be a scalar, it could be whatever we want it to be. Right? So here, the v's individually are different vectors. Okay? So let's work through a concrete example of three vectors, like, I don't know, in 2 dimensions. Let's look at some examples of linear combinations of v1, v2, and v3. How many linear combinations are there of v1, v2, and v3? Infinitely many, right? I could do any number times this, plus any number times this, plus any number times this, and the result will be a new 2-dimensional vector. Okay, the key is no matter how many 2-dimensional vectors I have, if I add and subtract and multiply, or add and subtract them, the result is always going to be another 2-dimensional vector. Okay? So if I do something like 2v1 plus, maybe minus v2 plus 1/9 v3, the result is going to be some vector in 2 dimensions. Okay, what specific vector would it be? Well, it would be 2 times this minus that plus 1/9 of that, and then it would be 2 times that minus that plus 1/9 times that. Okay, are we comfortable with how we would figure out what specific numbers would go in this vector? Okay. There's infinitely many of these linear combinations I could write, though, like I could do v2 minus v3. That's a valid one. You may say, hey, where'd the v1 go? Well, I could do 0 v1 plus infinitely many. Sound okay? A linear combination of a set of vectors is just a vector you can make by adding and scalar multiplying the other vectors. Sound okay? All right. So why do we care about linear combinations? Well, we really care about them because of the idea of a span. Okay? The span of a set of vectors is the set of all other vectors you can reach just by using those vectors as building blocks. Okay, so the span of 2 vectors is the set of all other possible vectors that I can reach just using those 2 vectors as building blocks. Okay? It's an abstract idea, but let's just work through a specific example. I'm going to make up some numbers here. v1 is 2, 1, and v2 is 5, 0. The picture in your head should look something like this. v1 looks something like this, and v2, something like this. The span of v1 and v2 is the collection of all vectors that I can make by moving in the direction of v1 a little and the direction of v2 a little, right? By adding, or by multiplying v2 by a constant, well, if I multiply by a positive constant, I can move any amount in this direction. And if I multiply by a negative constant, I can move any amount in this direction. Similarly, if I multiply v1 by a positive constant, I can move any amount here. And if it's a negative constant, I can move any amount here. And since I'm adding these two, I can make any vector by going some amount this way and some amount that way. Or I can make, that's how I make vectors, by moving some amount here, and the remainder I get by going there. Okay, so maybe one way to think about it is pretend you had two infinitely long roads, one in this direction and one in this direction. Well, no, roads are fixed. These you can move in either direction as much as you want, whenever you want. Like I can do this and then this. And then this and this too. And that would end up being a vector in the span of this one. Right? So like if you're not convinced, can I make this vector? Can I? How would I reach this vector? Yeah, well, I'll go here and then here, right? And that would make that one. Right, all I need to be able to do is move some amount here and some amount here. So it turns out that v1 and v2 span all of R2, which means you can recreate any vector in 2 dimensions by traveling some amount in the direction of v1 and some amount in the direction of v2 and adding together what you get. Okay, and this was the idea that like I wanted you to watch the 3 blue, 1 brown video for, so still watch it after class. Okay? But that's the key idea. The span of some vectors is the set of all other vectors you can make using them. So here, the span of v1 and v2 is all of the 2-dimensional vectors I could ever make. Do we agree? Okay, so as an example, I might say, let v1 be 2 and negative 3, and let v2 be negative 1 and 4. Is 9 and 1 in the span of v1 and v2? Firstly, before reading the if so part, the yes or no part, is 9 and 1 in the span of the first 2 vectors? You don't have to do really any calculation to know. Is it? Yes. Why is it? Yeah. Exactly. The only way the answer to this question would be no, assuming they're not 0 vectors, is if the 2 vectors pointed in the same direction to begin with. So by adding the second vector, you don't get the ability to move in a different direction. But as long as, in 2 dimensions, they point in slightly different directions, you'll be able to recreate any 2-dimensional vector. Do we agree? The 2 vectors, they can be as similar as you want. Like one can be this and one can be this. But still, you can move up and down as much as you need to recreate any other vector. Do we agree? Okay. And so, the answer is yes. We can. There and v2 aren't scalar multiples. They point in different directions. Okay, so if so, write y as a linear combination of v1 and v2. Well, what that's asking me for is for some weights, which I'll call w, such that w1 v1 plus w2 v2 equals 9, 1. But since v1 is 2, negative 3, this is asking for this. And since v2 is negative 1, 4, this is asking for this. Okay? And if I do this vector sum here, I pull out these two. That gives me 2w1 minus w2 equals 9. And these two, negative 3w1 plus 4w2 equals 1. And I can solve for w1 and w2. Okay, I'm not going to do it here. It involves, just multiplying this first equation by 4, adding it to this one, rearranging. The numbers were supposed to turn out nice, but I think I made a typo and they didn't turn out nice. Like one of the answers is 37 over 5. Whatever, that's not the point. Like if this ever came up, the numbers would be nicer. Okay?